Okay, great. Yeah. Okay, so yeah, I'm very happy to have this opportunity to talk to all of you about ground-based observatories in India. And as you'll realize, that's a mammoth task to to cover all the ground-based observatories in India in the half an hour or 35 minutes which I have. But I'll try to do my best. And of course, I'll have to be a bit selective about the ones I talk about. But before we start to talk about the ground-based observatories, I just wanted to take a moment or two to share with you some personal reflections uh, from me about you know what got me into astronomy, or why I'm still doing astronomy, or why I'm so passionate about astronomy. Right? So if you think about it, really, the only assumption which astronomers make when they are studying the universe is that the laws of physics are same everywhere in the universe. Whether we are in our solar system, or in our own galaxy, or nearby clusters of galaxies, or the furthest reaches of the universe, the laws of physics are all the same, and the fundamental constants of nature, like the mass of an electron and the gravitational constant, etc., all of these guys, they also have the same value. That is really the only assumption which we are making as we are studying the universe, right? Then if you think of the limitations under which astronomers operate, they are enormous, right? As compared to, all other branches of science which you are aware of. We cannot usually go to the places which we study. Fine, I mean, we can go to the moon and Mars and so on, but that's about it. That's the extent of our ability to visit our places. We cannot hold usually any samples of the things which we are studying in our hands. We cannot do the kinds of experiments which we do in our physics and chemistry labs, where you hold all the other parameters constant, but just let one parameter vary and try to discover the laws of nature. And I cannot even usually take a look at the object which I'm studying from a different vantage point, right? I'm stuck to the earth. That is where I'm going to be observing from. And that is the only perspective I'm going to get on that object. So the only thing you can do is really wait for the light to come to your telescope. And that is what you're going to analyze to, understand whatever you can learn from it about the universe. Also keep in mind that the light which you are going to receive is actually a very faint signal, right? So that is the reason why astronomers build telescopes. You build larger and larger and larger telescopes so that you can detect fainter and fainter signals and understand them in greater detail. Okay. So, to me, astronomy is really the embodiment of science of very accurate measurements, right? I have something really tiny, but I have to measure that very accurately and with great precision. And then to interpret that, I have the framework of physics which is available to me. So that is a little bit like playing Sherlock Holmes, right? The murder has been committed. The evidence is in the form of the light which your telescope has measured. And now you have to use your logical deduction in this framework of physics to figure out, what must be the situation at that place. And that is really what I find enormously empowering about astronomy. That is what got me into astronomy, and that is what still keeps me fascinated about astronomy. And there is one more aspect which, as I've sort of grown older, I guess I begin to think more about, which is that, you know, doing astronomy makes you humble, right? If you look at the picture which is there on the right, it's called the pale blue dot. If you're not already familiar with it, I urge you to look it up on the web. This pale blue dot which you see is actually the Earth, which was a picture which was taken on the Valentine's Day in 1990 by a satellite by the name Voyager 1, right? That's home. That's where all of us are, right? And this is a much earlier picture taken off the Earth from the moon by Apollo 11 astronauts. And when you look at this Earth, you don't see any boundaries of countries, you don't see any colors of skin, you don't see any differences in culture or whatever. There is nothing which divides us, right? All this is home. This is where all of us are. And similarly, when you stand on the earth and look up at the sky, again, there are no boundaries, right? There are no countries, there is no proprietorship. And all of us are trying to understand the same sky, the same universe. And that I think is actually a fantastic, tool which unifies all of us. And that I think is something which we need more of in our world today. Okay, so with that preamble, let's get to what I'm really supposed to talk about, all the telescopes in India, the ground-based telescopes in India. So, of course, you're all already familiar with the electromagnetic spectrum. It runs all the way from radio waves at the large wavelength end all the way to gamma rays, right? And these lights are the messenger, these electromagnetic radiation is, uh, is the largest messenger which we use, which is bringing to us information about the rest of the universe. And in this plot, you can see the wavelength mentioned and the corresponding frequency. And there is one more thing which is mentioned at the very bottom, which is, if this light was coming from what we call a black body, right? You just heat something up and look at the peak at which this body is going to radiate. So the peak of that spectrum depends on the frequency. The higher is your frequency, the hotter is that object which is going to give out that light. And this is just to give you a glimpse for why do you want to study the universe in various wavelengths in the first place. Okay, so we are going to talk about ground-based telescopes. So that naturally means that I can only study the light which comes to the ground, right? And that is what is shown in this top plot here. It is the axis on the y-axis is the quantity on the y-axis is atmospheric opacity, and on the x-axis, it is the wavelength. The same thing is shown a little more pictorially in the bottom panel as well, right? And this is the visible part of the spectrum where, we all see, and that is where the sunlight penetrates the atmosphere and gets down to us. And you notice that at the smaller wavelength or higher frequency range, actually the atmosphere has become practically opaque, right? Very quickly here, the opacity reaches 100%. Similarly, as I go to longer wavelengths, there are a lot of regions, in the infrared and so on, where I have rather high opacity. And then there is this large radio window where a lot of the waves from the universe or from above the atmosphere can penetrate the atmosphere and make it to the ground. And then at roughly wavelengths of around 10 meters or so, uh, our ionosphere begins to block the radio waves which are coming in here. And so this atmospheric opacity really defines the windows in which we can observe the universe from our ground. And that limits, what are the frequencies in which you are going to build these telescopes as on the ground to study the universe. Okay. Okay. So I alluded just a little while ago to why should we look at why is there even a need to look at the universe in any other wavelength apart from optical? This is an image just to highlight that, though none of these have been actually taken by ground-based telescopes. The image on the left is by Hubble Space Telescope in the visible part of the spectrum, and that on the right is by the James Webb Telescope in the infrared part of the spectrum. Now, as you look at that, you notice so many differences and also some similarities, right? The infrared image is absolutely full of stars, while the most prominent thing in the visible image are these, dark things which were, originally called pillars of creation when they were first photographed. And what is happening here actually that this region is full of dust. This is sort of nurseries where new stars are being born. And at infrared wavelengths, that light is able to penetrate the dust. So you are actually able to see all the stars which are hiding behind that dust, almost all, because there are regions where the dust is so much actually, for example, where my cursor is, that you are not able to still see the stars there. But as is extremely evident, the number of stars you can see here is a lot more. So the image on the left tells you a lot more about the dust, and the image on the right tells you a lot more about the stars which are, hiding in that dust. Here is another example of Andromeda, which is the nearest galaxy to ours. At the very center is the visible image. To the left of that is the infrared image, something similar to what I showed you from James Webb. Further left is radio. So in the visible, what you see is typically the starlight. In the infrared, it is the dust around these stars which has been heated up, and that is what you're seeing. In radio, what you're seeing is primarily the hydrogen gas. It is not evident here, but often these, in radio, the size of the galaxy is much larger because the hydrogen around that galaxy goes well beyond the regions where stars are distributed. As you go to shorter wavelengths or higher frequencies on the ultraviolet side, you see stars which are actually much hotter than the ones which are visible, which are prominent in the visible disk. So therefore, you see that the number of bright points here is much smaller than those in the visible, because it's only the bright stars which you can see here. And as you go to X-rays, these are some really special objects which have the capacity to heat things a lot. These are typically either black holes or two objects going around each other in very tight circles, which have the ability to heat matter to extremely high temperatures. So if I want to study, any given object, all aspects of it, I must look at it in all the different wavebands. And that is why astronomers do what we call multi-wavelength astronomy, right? You look at the same object in all the different parts of the electromagnetic spectrum, so you can learn the most about it. Okay, so about the ground-based telescopes in India, the image on the right is actually just a sort of catalog of all the various places where either astronomy was being done, telescopes existed, or there are institutions and telescopes which are doing astronomy now. As you can see, that's a large number, and it is not feasible for me to cover all of them. So I'm going to give you some, small but reasonable sampling. So we have actually a good number of optical telescopes, some radio telescopes, and even some gamma ray telescopes. Even though I just told you that gamma rays cannot make it down to the surface of the Earth, there are clever techniques which allow you to actually study gamma rays. And historically, solar telescopes have been put in a category of their own. So I am therefore also just following the same convention. I have put solar telescopes in a category all by themselves. Let me just quickly tell you about those, right? So the ones in India, the various institutions which are running solar radio telescopes are primarily the Indian Institute of Astrophysics, IIA, which is located in Bangalore, and the Physical Research Laboratory in Ahmedabad. Sorry, I forgot to mention that here. So this is an image of the Kodaikanal Solar Observatory. This is actually the longest running observatory in the country. And in fact, this year it is celebrating 125 years of its operations, right? This is an image from the Gauribidnur Radio Observatory. So this is studying the sun as well as doing a few other things. Actually, Kshitij, my colleague here, also worked on this array for his thesis here. So this studies the sun and a few other objects at very low radio frequencies. The Udaipur Solar Observatory, run by the Physical Research Lab in Ahmedabad, is actually, as the name suggests, located in Udaipur. Not only that, it is located in the middle of a lake called the Fateh Sagar Lake. And there is another solar telescope called the National Large Solar Telescope, a 2-meter class telescope, which is currently proposed to be built on the banks of a lake called Pangong So in Ladakh region. Okay. Okay, coming to the optical telescopes in India. Again, here is the list of the major institutions which run optical observatories. The first one again is Indian Institute of Astrophysics, IIA in Bangalore. They run 2 observatories, the Venu Bapu Observatory in Kavalur, the Indian Astronomical Observatory in Hanle, Ladakh. The next major institute for optical astronomy in our country is the Aryabhatta Research Institute of Observational Sciences, referred to as ARIES, which is located in Nainital. They also have a couple of campuses where they run observatories. And the third one again is PRL Ahmedabad, which runs an observatory in Mount Abu. Okay, let me tell you a little bit more about the first 2 of these institutions. So IIA is actually among the largest and the oldest institutions in the country, which is doing astronomy. Okay, so roughly about 150 scientists, about similar number of engineers, roughly 100 PhD students. Right? And the observatory which I was mentioning, the Kodaikanal Solar Observatory, was actually started operating in Kodaikanal in 1899, and so it's celebrating its 125th year here. And IIA itself got its current name in 1971, so it's again a 50-plus-year-old institution. Okay. The Venu Bapu Observatory in Kavalur is, you could say, it is the oldest modern observatory to be set up in Kavalur. It hosts a large number of different telescopes. The diameters of these are given below. The largest one has a diameter of 2.34 meters, and there are other smaller ones also, but these are the ones which are actively used for research in Kavalur. Okay, and on the right you see, on the left you have a picture of the 2.3-meter Venu Bapu telescope. Professor Venu Bapu was the first director of IIA and who actually got this telescope here in the first place, and now it is named after him. And on the right is just an aerial view of the observatory. So I have here a little bit of a shot of the observatory. So as you see in this small clip, it's essentially a forested region. There are these small domes which are distributed all over the place, but much of it is forest, and you don't have many neighbors. And you really need that because just to lead our normal human lives, the light which we use, right, gives rise to light pollution, which makes it hard for the observatory to function. Okay. Here is the other observatory which is operated by IIA. It's called the Indian Astronomical Observatory, and it's located, at 4,500 meters above mean sea level, which is more than half the height of the Everest. Right, so you can imagine that it's a pretty tough job to be working there here. And the reason why astronomers like to go to such heights for building optical observatories is because then most of the atmosphere is below you. And it is the distortions in the atmosphere which distort the image of the astronomical object which you are trying to image. And therefore, by going to a higher height, you can get much better imaging quality. Okay? So the telescopes on the left are the 2.3 meter. This is a 2.3 meter HCT, or the Himalayan Chandra telescope. And this is a smaller Growth India telescope, which is a robotic telescope. There are also a few other observatories here. These are the gamma ray telescopes. So let a movie run as we talk about this, right? So this is again a drone shot of the Himalayan Astronomical Observatory. This is the largest telescope there, the 2-meter HCT. And to do astronomy with a telescope, you need not just a mirror to collect the light, but also something which will receive that light and analyze that. So now, depending on if you want to make an image or you want to look at the spectrum of the object you are interested in, you are going to use different what we call backends. And what were being mentioned just now were these backends. What you have on the screen now is the robotic telescope, which actually operates without any person being on site. Its job is to look for transients, and whenever a transient is reported, it goes looking for this. And this, let me just pause here if I can. No, I cannot. Okay, so let's run this again, and okay, what you see on your screen now is something called MACE, Major Atmospheric Cherenkov Experiment. Now this, and actually some other telescopes which were being shown here, things like this. These telescopes are actually used to image gamma rays. How? What happens is that as gamma rays are propagating through the atmosphere, actually quite high in the atmosphere, they give rise to pair production. An electron and a positron is born. And that carries the energy of the original gamma ray. And because of that, it is moving so fast that it gives rise to something called Cherenkov radiation. If you would like to know more, you should really look up what is Cherenkov radiation. And it's something very interesting. But by looking at that Cherenkov radiation, you can actually figure out the properties of the original gamma ray, which gave rise to the burst of light, which lasts just for a few nanoseconds. And by that, study the gamma rays. Okay. So the other institution which I wanted to talk about, which runs optical telescopes, that is the ARIES, or Aryabhatta Research Institute of Observational Sciences. Right? Their original campus was at Manora Peak, not so far from Nainital city, and a more recent campus is at a place called Devastan, which is much further out. And here is the reason why actually they had to go to a different campus, because when, this is the Manora Peak campus close to Nainital, and you can see this Haldwani city in the plains. So when this was built, a lot of this was empty. But now, as more and more population has come there, the light pollution has become worse, and so they have moved to a larger site, and that is where they have set up the better instrumentation. This telescope at Manora Peak, this was set up in 1972, is actually a twin of one of the telescopes which was there at the Venu Bapu Observatory, which IIA has set up. This again is, I don't want to get into the technical details mentioned here, but the idea is just to show that depending on the size which you want to do, you are going to choose a different backend. If an imaging camera, if I just want imaging, or a polarimeter, for example, if I want to study the polarization of the radiation which is coming in. Here is an aerial view of the uh, the Devastal campus. This is the 2.6 meter, is the name not appearing? Yes, sorry, 3.6 meter Devastal optical telescope. Here is a smaller telescope which was set up much earlier there. And this is an extremely interesting instrument called the International Liquid Mirror Telescope, which has a diameter of 4 meters. So let me just, okay, let's skip this. But here are the different backends which are available for the 3.6 meter telescope, which essentially, I mean, for our purposes, they allow you to look at spectra or images ranging from optical to infrared. That is really the thing which I want you to take away from this. And this International Liquid Mirror Telescope is actually a very comparatively novel and very interesting idea. So what you have is actually a very stable platform, which you can see here. On that, you pour about 50 liters of mercury and you spin it at a rate of something like 8 rotations per minute. And that rate of rotation is sufficient for the mercury which you have put there to organize itself in the shape of a paraboloid, which now you can use as a mirror. It comes with some limitations that you cannot point it in any other direction, right? You're always going to be pointed towards the zenith. So such telescopes are called zenithal telescopes. Here is what that mirror looks like. You see some lines running through. This is actually some very thin sheets of plastic which have been placed over the mercury so that to contain the mercury vapor. Before the telescope would be used, actually these would be taken out. This is put in just when the mercury is poured. So this is a comparatively new telescope, and it's actually the largest of its kind in the whole world. And here is the first light image from April of 22nd. Okay, and as you can see, the imaging quality is really beautiful. Okay, so apart from optical, I had mentioned earlier that actually the largest window which we have in the electromagnetic spectrum lies in the radio part of the electromagnetic spectrum. And the two institutions which run the radio observatories in the country are NCRA, National Center for Radio Astrophysics, where I come from. And we have two facilities which I'll tell you about. And the other one is IIA, which runs an observatory at Gauribidnur jointly with the Raman Research Institute, which basically this is a low radio frequency observatory, which operates largely in the range from about 40 to 150 megahertz. I'm going to primarily tell you only about the first. Okay, here is the Ooty Radio Telescope. It's a spectacular site. It is located, as the name suggests, close to the town of Ooty in Tamil Nadu. It is 530 meters by 30 meters in size. So it's more than half a kilometer in size, and the whole thing can move. And it's a very clever design which led to this telescope. So this was built by Professor Govind Swarup and his team, and they spent years looking at the maps of southern India to look for a hill whose slope is in the north-south direction and has a slope is roughly equal to the latitude of the place, which in this case turns out to be 11.2 degrees. So what that allows you to do is that if I just put one linear telescope there, my axis of the telescope has now become parallel to the axis of rotation of the Earth. So I need to compensate only for the rotation of the Earth to be able to track a given direction in the sky. And that was the beautiful idea which was implemented here. And so even though this is almost 54 years old now, this telescope is still the world's largest steerable telescope, single steerable telescope, right? And the whole thing is driven by just one shaft, which you can see running along the telescope here. Okay. The other telescope, which is really the pride of the nation, is referred to as the GMRT, or the Giant Meter Wave Radio Telescope. In the frequency range of its operation, in most of the frequency range of its operation, it's actually the world's most sensitive radio telescope. People from more than 30 countries use this telescope. It has recently completed a major upgrade where basically everything apart from the steel and the concrete of the antennas, the entire signal path has been upgraded. It's recently also been recognized by IEEE, International or Institute of Electrical and Electronics Engineers, as a milestone. It's just the third one in India and actually the first one after independence. So what is this telescope? Here is one of the GMRT dishes, right? Each of these dishes is 45 meters in size. There are 30 of them. As this video shows, this is a fully steerable dish. It can be pointed anywhere in elevation and azimuth. And actually, all the dishes can be made to work simultaneously. So the whole thing works like a single telescope, even though there are 30 of these dishes spread over something like 28 kilometers. Now, this just shows you the close-up of the apex of the dish. So the dish region, actually, you can barely see it here. There is a very fine mesh, which is acting as a reflector of these radio waves. And all the radio waves which are being reflected by that mesh are being concentrated at this apex point where there is this feed, which I'm hoping will come into view shortly. Yeah. Which is this point, which is actually collecting all these rays which are being brought into focus here. And by choosing different uh, feeds, as we call them, you can choose to observe at different frequencies, and that is how GMRT is able to, observe all the way from 150 megahertz to 1450 megahertz. So if you look at the layout of the GMRT on the ground, this is what it looks like. Right? It has 30 dishes. 12 of them are clustered together in the center within an area of about 1 square kilometer, and there are 6 dishes in each of these arms, right, which are spread roughly in the shape of a Y, which give rise to a telescope which is about 28 kilometers in size. And like I said, this is one of the most sensitive telescopes in the entire world. Okay. Now, in addition to the telescopes which are there on Indian soil, there are many others now which India is a part of. And these are mostly under construction right now. And these are large international projects, right? So the one on the screen right now is something referred to as the Square Kilometer Array Observatory. Actually, 12 countries are coming together to build this telescope. In fact, it's not a single telescope, it's 2 telescopes. And what you have is actually an artist impression on the screen. On the left is what will be the Square Kilometer Array Mid. It is being built in the Karoo desert region of South Africa, and it will cover a frequency range from about 500 megahertz to 15.4 gigahertz. On the right, you have an image of the Square Kilometer Array Low, which is being built in the Western Australian outback region, and it will cover a much lower frequency range, 50 to 350 megahertz. So these telescopes are actually currently under construction. The work is going on at a very brisk pace. The early science operation is expected to start by 2027, and the full science operation by 2029. Right? And on the movie which has just started to play is actually the first image from the first SKA low station, which is showing you the full sky, the full hemisphere of sky above you. This is the galactic plane, which is rotating. And I did not point it out earlier, but the sun will come up here. This is the sun here, which is moving across the sky. These are some other bright sources which are coming into view. And as the Earth is rotating, these guys seem to be rotating in the sky as well. And here is the galactic center back in view. And this is just to show basically that work is really happening on these. And by the time you are finishing your master's degrees or something like that, you can expect a telescope like this to be available to you. That was the radio telescope, and here is an optical telescope, which India is a part of as well. Again, I don't remember the number of countries, but some more than 10 countries are a part of this international observatory. It's called the 30-meter telescope. As the name tells you, the diameter of the mirror is going to be 30 meters. We're still choosing between where to build it, and the site selection is expected to be finalized by 2026. Okay. And here is another one. This is again an international project, but will also be built on Indian soil. So the site for that has been selected. It's in the Hingoli district of Maharashtra. This is a laser interferometric gravitational wave observatory. So all the other observatories which we talked about till now, they are all working in the electromagnetic part of the spectrum. However, astronomers now get information about astronomical sources from sources other than electromagnetic radiation as well. So I wanted to include at least one example, and that is this guy, LIGO. Because I'm sure you've all heard about the discovery of gravitational waves, and these days it's quite common to hear about a new discovery or a new measurement of these gravitational waves. And the whole idea of building one in India is to improve dramatically our ability to figure out the direction from where these gravitational waves are coming. right? So that's mostly what I wanted to share with you. I'm sorry I've been rushing through. That's primarily because I had a large mandate to cover a lot of ground. But the thoughts I want to leave you with are the following, right? Historically, India has had a very rich legacy of ground-based observatories, right, from Jantar Mantar to more recent ones. And Indian astronomers have continued to build and operate really truly world-class radio and optical observatories, right? So we had a lot of legacy, and we have been building on that legacy as well. And now that we are entering a regime where the best instruments are all going to be international collaborations. So we are investing strategically in the best of the next generation international facilities, so that you know when the next generation of scientists they come up, they will have access to cutting edge data, which will enable them to do the best possible science, the cutting edge science, right? So I think it's really an exciting time to be thinking about, astronomy as a career option, especially if you like physics and maths. This is probably a good time to be thinking about these things. So with that, I'll stop and I'll take any questions which you might have. Yeah.